Granada. He studied physics. Then he came to Madrid, to the University Complutense, where he makes an experimental thesis. And after that, he continues working in the University Complutense, where now he's a full professor, he's catedrático there. He has been in Bologna and also in Barwith for long stays. And now he has a group, and the name is nano-electronics or something like that. He's an expert in electronic properties of a small system. In particular, I remember a lot of papers about transport and electronic properties in one-dimensional disorder change. Mm-hmm. Okay. He has published a lot of papers in prestigious journals, and has collected a lot of citations and things like that. So he's very smart. And today he's going to tell us about this electronics hydrodynamics in conventional fluids. Okay? Thank you.
Okay, it's a big pleasure to be here today. So for that, I would like to thank, first of all, the organizers, in particular Luis, for the kind invitation to present this talk. Today, I will be talking about a particular transport regime of electrons in 2D materials, which is known as the hydrodynamic regime, in which the electron-electron interactions are very important. So, sorry, just testing, okay. So, as I said before, this is a particular transport regime. We have been working on that only the last 3-4 years, so we are not really experts on that, but it's because it's a very complex problem, as I'm going to convince you, hopefully. So the idea is that when you reach these conditions, the electron system behaves like a common fluid, like water. But of course, we are not dealing with classical particles like water molecules, but quantum particles. And this difference is very important for understanding some peculiarities of the electron fluid in transport measurements. So there are some specific signatures in the experiments in which you can see that the electrons are behaving this way. So for instance, superballistic conductions, Poisson flow, whirlpools, and anomalous thermoelectric responses. I am going to discuss all these topics, so don't worry too much about the details now. Oops. So the outline of the talk will be as follows. First, I will give you an introduction, a broad introduction for those of you who are not familiar with the problem. So Alberto, you can sleep for a while now. And then I will discuss how you can obtain hydrodynamic equation from the Boltzmann equation for semiclassical electrons. And then I will then go to two works we have been doing in the last years. And finally, I will discuss the thermoelectric response of the hydrodynamic electrons. We have not made any contribution in this topic, but these thermoelectricity problems are very interesting for us in other contexts, so this is why I'm going to tell you something about that in the talk, and I will end up with some conclusions. So, let's get started by introducing the main ideas. They're very basic. So, when you are thinking in a transport experiment in low-dimensional systems of semiclassical electrons, you basically need to consider three length scales. The first one is the so-called elastic mean-free path, which is essentially the mean-free path due to the electron-electron collisions. It is called elastic because the momentum of the system, the total momentum of the system, is not changed. This is important. So this will not induce resistance in the transport. And also, a very important parameter here is the momentum relaxing mean-free path due to collisions with impurities or any other kind of defects, and also phonons. And this is the situation when the momentum is not conserved, it's transferred to other systems. And of course, in any small system, you need to consider the size, essentially. These are the three main length scales we are dealing with today. So, when the temperature is low enough, there are essentially no phonons, very few defects, I mean a clean sample, what you see is the so-called ballistic transport regime. Electron can collide with the edges of the sample. So this is very well known. In the opposite limit, here, when you increase temperature and there are defects in the material, electrons collide a lot with these defects and these phonons before reaching the edges. And this is the so-called diffusive transport regime, which is very well described by the Drude model. But there is another possibility here in the middle, on the left, in which the electron-electron interaction is so important that the smallest length scale in the system is this one, the elastic mean free path. And you see that the electron have a lot of collision before reaching the edges. And this will reduce the resistance. I will hopefully convince you that this is exactly the case. And this regime is called the hydrodynamic regime, which is the focus of our talk today. And this was actually predicted by this Soviet Union researcher many years ago. As you see, the prediction is very, very old. And the idea is that when you reach this condition, when the elastic mean free path is the smallest length scale, you will see at intermediate temperature a reduction in a metal of the resistance, which you don't expect that according to the Drude model. So this was a theoretical prediction, but at the time was essentially impossible to measure this in a common metal. But the advent of new materials, especially in the case of 2D materials, changed everything. So now we are able to test these ideas in the experiment. And this is what I am going to tell you about today. So just to put some numbers, these are estimations collected from different sources of the two length scale. On the left here, you see the momentum relaxing mean free path due to collisions with impurities and phonons. And there, you see the elastic mean free path due to electron-electron collisions. In the case of graphene, you see here, encapsulated graphene with a low number of defects, for 3 different electron concentrations and as a function of temperature, which is written here. And you see that inside this frame here, in all cases, the elastic mean free path is smaller than the momentum relaxing mean free path. And this is what you need in an experiment. And similar comments for 2D electron gases in gallium arsenide heterostructures. In this case, temperature is much lower. Notice that in the case of graphene, you will see this between 100, even room temperature, is not very low. But in the case of gallium arsenide heterostructure, you need to cool down the sample. But the situation is basically the same. And also there are other more exotic materials like palladium cobalt oxide. This is 3D, but electrons move in the metallic plane. So basically it's also a 2D material for these purposes. And you see basically all the same. In this case, you get this condition. So we have some materials in which we can test these ideas. I am going to discuss basically encapsulated graphene in case I forget to say something, but remember that there are other possibilities now available in the literature. So this is an example. I am going to show several very beautiful experimental results. This is one related to the so-called superballistic conduction. I am going to explain what this is now. And as you see here in this optical micrograph, you see here a graphene channel with several constrictions, quantum point contacts. By the way, this experiment was performed in Manchester, the group of Andrei Game. Yes, thank you. on the left, you see here the predicted electron trajectories, semiclassical electron trajectories, and on the right you see the experimental results. As the resistance of the quantum point contact as a function of temperature. And you see that at very low temperature you have the ballistic limit, but as soon as you start increasing temperature, the resistance goes down. And this is called superballistic because there is a better conduction compared to the ballistic limit. And this is very curious. And this is exactly due to the interaction between electrons, as I explained at the very beginning. This is actually a wonderful example. Here on the left, you see a parabolic profile, but I am going to discuss this in the next slide. So let me move to the second example. This is again graphene. You see here the system, and using a carbon nanotube single electrode transistor, they were able to map the current density in both in the longitudinal direction. Sorry, in the transverse direction. Sorry for that. It's the transverse direction along the y-axis. You see here the y-axis. At low temperatures, 7.5 Kelvin, you see that from the current you can obtain the whole field, and this is flat. And this is what you expect in the ballistic limit. But as soon as you increase temperature, here is 75 Kelvin, close to the temperature I mentioned before, you see a parabolic profile. And then you can perform simulations. And that's it. So you can compare your prediction with the ballistic theory, and you see this is flat, in perfect agreement with the experiment at low temperature. But as soon as you increase temperature, you can use Navier-Stokes equations. I'm going to tell about them in a minute. And you see this parabolic profile, again, in perfect agreement with the experiment. So this is another clear signature of the hydrodynamic transport regime, and this is called in conventional fluid the Poisson flow. It's parabolic. Oops. And this is another very beautiful example performed in Zurich. It is more recent, published 2 years ago. The idea is basically the same. You have a narrow graphene channel, but in this case they attach a couple of cavities, like this one, so the electron can flow from the channel to the cavity. And using a very complicated technique, which is based on, which is based on this nitrogen center close to a vacancy, and then measuring locally the magnetic field. From the magnetic field you can obtain the current density. And here you have the experimental results. The left column is the experiment. In case you cannot see it, it's the current in the two directions, transverse and longitudinal. And you see on the right 2 columns with the hydrodynamic simulation, the middle column, and with the diffusive, basically the Drude model on the right. And you see that the agreement, this is clear here, compare these 2 panels, the agreement is excellent. So again, this is another proof, the existence of these whirlpools, when you have these kind of loops inside the cavity, that the electrons are behaved collectively like a fluid. And let me finish the presentation of the experimental results, which are not ours. Talking about a very curious device, which is called the Tesla valve. The Tesla valve is due to Tesla. You know Tesla. And he was thinking in obtaining a non-reciprocal pipe for water, in which the flow from one direction is different from the flow in the opposite direction. He was thinking on that based on the nonlinearity of the hydrodynamic equations. And in this case, it's important to notice that we are talking about phonons, not electrons. We'll be dealing with electrons, but this is for phonons. And again in graphene, and they did exactly the same. They put a hot sink, a cold sink, and then change the temperature to obtain the thermal conductivity in the reverse direction. They plot the ratio between the two as a function of temperature here. In this area, which is the expected area of, the temperature window for the hydrodynamic behavior of phonons, not electron, phonons, you see here an increase of the diodicity. You are having different thermal conductivities depending on the direction of the flow. And to check this idea, they also put another material, silicon oxide, do exactly the same experiment, and they see nothing, essentially 1, which means you are not getting this effect. So this effect was related to the collective behavior in this case of phonons. If you think about electrons, the situation is not so clear, unfortunately. This is a paper in the case of electrons. The idea is the same. You put several Tesla valves and measure the current from one side, moving from one side to the other side. Well, the situation is not so clear. Actually, if you look for the paper, you will not see it. So probably the paper was rejected somehow. So the experiment is still pending. So if you are lucky, you can check this prediction. Probably has to do with you need nonlinearities. I'm going to discuss nonlinearities at the end of the talk. Nonlinearities are difficult to obtain in a real electronic system. Maybe not in the case of phonon, but in the case of electron, you have problems to get in this. So maybe this is the main difficulty in the case of electrons, where you are not seeing any non-reciprocity here. So these are some experiments among many others in the literature. And let's it should be much smaller. Well, let's go to the basics, the fundamentals of the problem here. So as I said before, we have 3 different length scales: the elastic mean free path, the momentum relaxing mean free path at the system size, and sorry for the symbol, here should be seen that this quantity on the left should be much smaller than the other 2. So if you think about the basic physics, sorry for the lecture on basic or solid state physics, we need interactions. So this will reduce the electron-electron mean free path. So we need Coulomb, for instance. So this is good. But electrons are not classical, they are quantum particles, obeying the Pauli principle. And you know very well that when you consider this problem, when you consider this principle, the possibility of having collisions, especially a very low temperature between electrons, is essentially nothing, because the outgoing electrons need to be in empty states, which are difficult to find if you are at very low temperature. So this is bad. And also in a real system, you have temperature. Temperature cannot be 0, so you have phonons, many or few, but you have phonons, and you have impurities, always, or defects. So this is also a problem, because these impurities will decrease this, and we don't want that. So these are the 3 main actors here. And now let me discuss how we can explain the hydrodynamic regime. When we started 3 or 4 years ago, before in the program, we realized that many people from the theory side use from granted the Navier-Stokes equations. So I'm going to show the equation now, but if you are familiar with fluid dynamics, you see, or you remember, that there are some parameters, for instance, the viscosity of the fluid. And at that time, this viscosity was a phenomenological parameter. You adjust this viscosity, which is a macroscopic parameter, comparing with the experiment. So I propose my student to go to the fundamentals of the Boltzmann transport equation for semiclassical electrons and try to get the Navier-Stokes equation. And he performed really very well, as I'm going to show you now. So don't worry too much, don't panic, I'm not going to enter into the equation, but this is the Boltzmann equation. For semiclassical electrons, the group velocity is, here I am going to be in the steady state, so we neglect the time derivative, the electric field, so this is the gradient of the potential, the magnetic field, and the important part is here in the so-called collision operator. All the physics of the interaction is there. So you need to be very careful when when discussing this. So as I said before, when we started that, we were not even familiar with the Boltzmann transport equation. So we went to the literature and found that many people use this two-time relaxation approximation. Due to Callaway, he used this approximation in the case of phonons, and we took the same approximation. Of course, we know that phonons are boson. Now we are dealing with fermions, but when you are not expert on that, you take the easiest situation. So we consider this. Notice that also we have here the Fermi velocity, because at not very high temperature, our electrons are moving very close to the Fermi level. So basically, all the velocities are the same, the Fermi velocity. So we introduce usual magnitudes, like for instance this effective cyclotron mass and the cyclotron radius, and you end up to this equation, which is the J function here is given by this expression. So we only need to integrate the Boltzmann equation as a function of the magnitude of the vector K. No, it's here, in this. It's here. It's assumed that they are affecting the distribution function in the relaxation time approximation. So the whole idea is to include two of them. I know there are many limitations because here you don't see the Pauli principle, for instance. I know that. So after some calculation, you end up with this couple of equations there in this frame for the drift velocity of the electron, the mean velocity of electrons in the fluid as a function of position in the fluid. And the first one is very well known. It's the continuity equation for an incompressible fluid. So this is something you expect. And the second one is more or less the standard Navier-Stokes equation. There are some differences. For instance, the nonlinear term is not here because we neglected it. But you know that in the Navier-Stokes equation for conventional fluid, this can be very important. And also, there is this term here, which usually is not in conventional fluids, and this has to do with the dissipation inside the fluid, because you are losing momentum due to the collision with impurities or defects and phonons. So besides this difference, the equation is essentially the same. And the important thing here, you see there in this term, the viscosity. And the viscosity now is not a free parameter. It's obtained from the microscopic details of the problem there. So we have an expression for the viscosity. This is one of the issues or the goals of the problem. And if you want to dive into the mathematics, you can check this publication there. So just to test the correctness of the Navier-Stokes equation, we made some simulation just for testing purposes. So here you see a graphene. This is for graphene channel with a constriction, quantum point contact there, and we measured the velocity profile solving the Boltzmann transport equation with this approximation, with the dual time relaxation time approximation, and also the Navier-Stokes equations. And in this case, you see, we set these parameters, so you are in the ballistic regime, essentially. So we, on the right, have the velocity profile at 2 points, just in the middle, on close to the quantum point contact. In any case, the discrepancy is clear. I mean, there is no agreement between them. And you expect that. So the message is don't use Navier-Stokes for the ballistic regime. This is one of the messages we are going to have after the talk. But if you move to the hydrodynamic regime just by changing this parameter, again, you can plot the profile, the velocity profile, and indicate the agreement is perfect. I mean, the curves overlap on top of each other. So this equation I showed you before is good enough to describe the situation in the hydrodynamic regime. So let's go back to the Navier-Stokes equations and remember that we have this term. So if you want to see hydrodynamic effects, you need to make this term very important. You cannot usually control too much the viscosity because depending on macroscopic parameters, you can set the temperature, of course. But the idea behind all this was to play with the geometry of the device. Why? Because this term contains the derivative of the velocity. So if you change, and you make the change of the velocity in a space large, you will have higher effects. This is what we thought. And this is the idea. You can play, for instance, with the edge of the channel. Instead of using a uniform channel, you can use this crenellated channel. And you see that you actually increase the effect of the viscosity. I'm going to discuss in detail later all this. So this is the idea. Play with the geometry to enhance the hydrodynamic regime. So let me then move to our first proposal of playing with the geometry. And the idea was the following. Why not take a graphene nanoribbon and then make some holes, make there some antidotes. So just simply remove graphene by using lithography. And before doing any experiment, which is expensive and time-consuming, we made some simulations of different arrays of antidotes. Square, circular, and also changing the direction of the ray with respect to the flow direction. And the winner was this configuration. Circular arrays, circular antidotes, inclined 45 degrees with respect to the direction of motion of electrons. So with this at hand, we were in contact with our co-workers in University of Salamanca. Sorry? Well, the idea is to check what. You mean what we look for in the? Yeah, that one.
Yeah, why is that one?
Because you see here that the curvature of the streamlines are higher, and you need curvature essentially. This is what the expectation. Oops, sorry. So we were in touch. Yeah, always. There is no pressure gradient of in the Navier-Stokes. That's true. Yeah, we have. Yeah, tell me. Yeah. Yeah. This is the carrier. Yeah, yeah, yeah. We have some results on concerning that, but not here. So, but you're right. All right. So this is sample was grown and designed and grown by our co-workers in Universidad de Salamanca, Enrique Díaz and Mario Amado, and you see here on the bottom the same micrograph of the resulting device. You see 3 different regions with an array of antidotes of different sizes: 300 nanometers, 200, and 100. And the separation between the antidotes is also exactly the same as the diameter. So this is why they are changing. And by this contact, they can measure this region is separated. This is important. So I'm not going. There are many experimental results, very complicated, at least for me. But let me show you one of the main pictures here in this work. These are the resistance of the 3 different regions of the sample as a function of temperature here. This is for the electron sector, for the whole sector by changing the gate voltage, and these are the simulations. So the idea is that when you decrease this, well, you always see the superballistic effect. Here is not so clear, but trust me, it is superballistic effect. And the main message here is that when you reduce the size of the antidotes and the separation between them, you see an enhanced superballistic phenomenon. And this is what we're looking for. If you want more detail, you can have a look at this paper and many other experimental results, very beautiful, by the way. So now let me tell you something about, sorry, just 1 second. Tell you something about the so-called superballistic paradox. The situation, the theoretical situation here is even much more complex than before, so I will comment on that very briefly. So the situation is the following. When you go to the theory proposed by Gursi and later obtain the same result, you expect this behavior of the resistance as a function of temperature in a sample in which you can hopefully get a hydrodynamic transport regime. So the idea is that a very low temperature, you are in the ballistic regime, maybe a little increase due to some phonons, but essentially flat, and then you expect a decrease when you enter in the superballistic conduction regime. This is exactly the same what you expect in common fluids, by the way. In common fluids, you deal with the flow, with the current, if you want. So it's basically the inverse of that magnitude, and you expect that when the mean free path of the molecule collision is on the order of the diameter of the pipe, for instance, you expect a minimum, which is known as the UCM minimum. So here we have a maximum because it's the opposite magnitude. Okay, this is what theories say. And this theory is based on the simple approximation for the collision operators. In particular, I'm not sure you can see it, but you are assuming that electron can collide coming from any direction, maybe almost parallel to perpendicular to head-on collisions. But if you think, as I said before, that you are dealing with fermions, you see, or you know, that the most important collisions, especially at low temperature, are head-on collisions because of the exclusion principle. So we decide to include this particular set of collisions. It's complicated. I mean, you need to expand the G function in terms of modes. And, well, it's more or less cumbersome. But the situation is that in the experiment you see always a decrease. At very low temperature, you always see a decrease, not a flat plateau or a small increase. So we try to explain this discrepancy by means of this, which is now called tomographic transport regime. Tomographic means head-on collision in this context. So here you have the simulations. The simulation, in the case you are considering any angle for the collision of the electrons. In this crenellity channel, this is a uniform channel, and then you are increasing the amplitude of the modulation on the edge. And you see that if you consider this kind of collision at any angle, you see an increase at the beginning, an increase of the resistance, and then a decrease when you enter into the hydrodynamic regime. But if you change your equations, make them more complicated, of course, and consider these head-on collisions, you see in the same sample as before, so we are only changing the equation, you see that always the resistance is a decreasing function. Different mean free path, yes, for different modes. Yeah, that's true.
Those are parameters.
Yeah, those are parameters. Yeah. There are some estimations in the literature, so it's not only our work, but the idea was that.
Due to the confinement.
No, to the confinement. No, to the details of the electron-electron scattering, taking into account that you are in a Fermi sea, basically. So details are given there in this paper published last year. So now let me finish with some comments about the thermoelectric response of the hydrodynamic electrons. As I said before, we did any contribution here, but I think it's very interesting, it's very curious. So let me talk for a while of this problem. So, again, I regret to go back to your history and tell about something that is well known for solid-state physics. So, if you think in thermoelectricity, which is a very old problem, 200 years or so, one of the main results at that time was the Lorentz number, which is defined this way, the thermal conductivity divided by the electrical conductivity and temperature. Phenomenologically, people check that this should be constant. And one of the success of the free electron model, the Drude-Sommerfeld model, was to explain that. It's a very simple calculation, trust me, it's for third grade year. And the results actually is that within this model of non-interacting electron, you get this value, which is universal, Boltzmann constant, charge, electron charge. So this is clear proof that this is the case, and this is well known in conventional metals. Basically, this is known the Wiedemann-Franz law. This value, the Lorentz number, should be constant for any metal. This is the idea. And then these people went to graphene, a very pure sample of graphene, and measured this Lorentz number. So you see on the left the Lorentz number in units of the ideal Lorentz number. Should be 1, but no, it's not 1, this ratio. Clearly, it's changing. This is for graphene for 3 different samples, and you see a huge increase at intermediate temperature between this range, this window. And the samples are different according only on the context of defects. So the cleanest sample wins. It's this one, sample 1, which is what you expect because the momentum relaxing mean free path is larger when you have less defects. That's it. And also there on the right, you see another experimental result, much more recent, in which they plot exactly the same quantity, but as a function of the electron density at 2 different temperatures. Low temperature or high temperature. And you again see a clear departure for the Wiedemann-Franz law, which is here, should be flat around there. It's not the case. Actually, they estimated that you have at the charge neutrality point an increase of 300 or something like that. It's huge. But I'm going to talk about that in the next slide. This is very bad for the performance of a thermoelectric device. You need exactly the opposite. But don't worry, don't panic. You can go there. You need electrons for having the hydrodynamic regime. So you need to be not very close to the charge neutrality point. So for instance, let's say this one. And in this case, you see a clear reduction compared to the ideal value here, several orders of magnitude. And this is what you need for improving the performance of a thermoelectric device. So the news are not so bad as expected. So let me then move to the last slide of this talk. Here you see the same results as before, just to remind you the results. And here you see the experimental results from an old paper. Here they are plotting the so-called thermopower or Seebeck coefficient, which essentially gives you how many degrees you can get by changing the voltage of the sample. This is the idea. And look at this magnitude. When you are thinking in the efficiency of a thermoelectric device, you think about the output power. This is one of the magnitudes typically used by people. And the other one is this quantity, which is dimensionless. The higher the value, the better. Actually, people say that you need at least a value of 3 or 4 there to compete with other well-established technologies. So you want to make money, increase this. This is the rule, the third rule. Okay, so let's go to the experiment, again in encapsulated graphene. And you see the experimental result. They are dividing by temperature, so these curves collide or overlap or collapse on a single picture far from the charge neutrality point. Here you see the electron density, and you have two theoretical predictions. The simplest one is the mode prediction, which is based on the single electron picture. I mean, there are no interactions to arrive in this formula. And using hydrodynamic equation, you obtain more or less a value which is double the mode prediction. So this is what we need. We need to increase thermal power. So interaction will increase the thermal power. So you see that the experiment in this case is more or less in the middle. It's a kind of mixture. This is the mode prediction, yes, and this is the hydrodynamic prediction for electrons, for holes. So the measure here is that you can move away from the charge neutrality point and increase the efficiency of the device. This is important, as I said, if you want to make money with this. So with this, I would like to finish with some take-home messages. The first one is that if you want to enhance the hydrodynamic regime, you need to bend the electron trajectories. This is one message, very clear. So you need to play with the geometry of the sample. The second message is that be careful with the Navier-Stokes equation many people use, because when you are approaching the ballistic limit, you are losing accuracy, that's for sure. I'm not going to discuss all of this, but basically the idea you can determine or calculate the error, and the error is clearly large in this ballistic sector. And also we have hopefully explained the superballistic paradox by introducing these head-on collisions. So we have explained why you always see, I would say 90% of experiment, a decrease, always a decrease as a function of temperature of the resistance. And just a few words about non-linearities. We have been neglecting non-linearities, and this is quite reasonable in the case of electrons, because non-linearities means high electron density, high current density, actually. So this is not easy to get in the case of electrons. But you can play with the current density to see this effect. For instance, by considering that the electron mean free path depend on the current, which has not been shown here, we can predict the existence of the so-called negative referential resistance. This is another paper we published a couple of years ago. And also you can play with your equation to make or to obtain a generalized Navier-Stokes equation in which nonlinear terms are there. We are working on that. Probably we will publish a paper, hopefully, in the near future. So with this, I would like to end the talk by thanking my co-workers in Complutense, Jorge Estrada, who is the brilliant mind behind all of this. We are very lucky of having this guy in our group. Elena Diaz, the co-supervisor of the thesis of Jorge. And from the experimental side, we are working hand by hand with the people in Salamanca, Enrique Diaz and Mario Amado, and now, sorry, I pressed the wrong button. And Juan Salvador, who finished the PhD, and he's moving now to Australia to continue with this type of work. And as always, sample work provided by these two guys. You know them very well. So with this, I would like to finish. So thank you very much for your attention.
Question and comment?
So if I understood correctly, your Navier-Stokes equation, you don't have nonlinearity.
Yeah.
In which case, I don't understand why it's Navier-Stokes.
It's a Stokes, probably, or something like this.
Stokes, right? Because you don't have all the physics of turbulence, of...
Yeah, no. The Reynolds numbers here, there.
It's closer to a diffusion equation, right?
Well, not exactly. It's similar to. I mean, we are not considering this affective term, you mean. People usually say this is the Stokes equation, usually. I'm not well familiar with fluids, classical fluids, but probably it's a matter of...
And I also didn't understand very well the role of statistics.
The
fermionic statistics.
Well, at the very beginning, we neglect about the Fermi statistic, yes. We only have into account this when introduce the tomographic regime.
So there is no interactions or no nonlinearity,
No, there are interactions.
but only in the kernel term.
Yes, there
Only
are.
this.
Oops. Interaction is here in this parameter.
Right, but
It's not,
but that doesn't make the equation nonlinear. This interacting term,
well, if you
because
take,
it's the
yeah, that's true. This is what they said exactly at the end. When you include or you think that these parameters depend on the current density, which is, in some cases, you have hidden some nonlinearities. Yeah,
Right.
that's true.
semi-effective nonlinearity.
Yeah, that's true.
And the Boltzmann equation, why is it so bad then in such a regime where you can neglect nonlinearity and don't need to take into account the fermionic statistics? What is missing from the transport equation, from the Boltzmann equation?
No, missing is this collision operator has all the information on the collision between electron and the
But the
static.
Navier-Stokes or the Stokes equation is an improvement from the Boltzmann equation, right?
An improvement? No, it's just the opposite.
It's worse. The Boltzmann is superior.
Yeah, sure. Even here.
Okay.
This equation can explain, for instance, the ballistic transport regime, which you see easily in an experiment when you go down to the experiment. So I would say that Navier-Stokes is worse than Boltzmann.
Less efficient, right?
Yeah.
And well, you also mentioned that you added the dissipation in the Navier-Stokes,
Yeah.
which is
This term, oops, sorry, just the other side. Here you have, this term coming from the dissipation. Because Navier-Stokes basically says that the momentum is conserved, which is not the case here because you are losing momentum by the collision with phonons or defects in the sample. This is why you get this anomalous term you don't expect in common fluids, in water, in a house.
I see. So as a summary, would it be accurate to say that what you are saying basically is that what drives the physics is the geometry and the dimension?
Yeah, that's true. Yeah, that's true. That's true.
Okay, Francisco, thank you for this talk. My question goes in that slide. So adding, or in the previous one, using the Callaway
Answer.
is
Yeah.
perhaps a bit problematic because
Yeah, problematic.
it's assuming that at the end of the day, this is momentum relaxing, in the sense that you have to check
count.
a posteriori that the momentum is conserved. This is related
Yeah.
to the question of Luis. So, because everything is momentum conserving, you have to check that the total momentum of your fluid
Yeah.
is conserved.
When you neglect this term, you mean?
Yeah, exactly.
Yeah.
So only with electron interaction you should get zero momentum
Yeah.
modification. So
I'm not sure that we check that exactly, but I think that this equation is actually what you find in common textbook, and there is proof that it's momentum conserving.
yeah, but
No, I understand. Yeah.
some people prefer to work not with this Callaway answer, but just for the full integral differential equation,
Yeah.
assuming that
Yeah. This is
it's a pain in the neck.
Yeah. This is something we are doing in the last year.
Okay.
I will give you a copy of the thesis
Okay, thank you.
where you will find a full chapter on that. Yeah, but you're right, totally right. Yes.
So I have a second question, mate. Yeah, this is also related to graphene because in many cases in graphene, if you are close to the neutrality point,
Yeah.
many people argue that you have two fluids, electron and holes.
Maybe.
And then you can construct two conserved quantities,
Uh-huh.
which is the total carrier density and the difference, which is not conserved, but is a kind of nearly conserved.
Yeah.
And the question is, you are not working in that region close to the
No. We
neutrality
are
point.
always far from the charge neutrality point. Always. I am not familiar what you say, but I trust you, of course. But we are working always in the experiment, at least far from the charge neutrality point.
Because this is perhaps relevant to the last part of the talk, where you have thermoelectricity and you
Yeah.
need to go to the. I mean, also graphene has electron hole paddles that can difficult a little bit what is neutrality point in the sample.
Yeah, this is why I said that. Oops. Oh, I'm going to the wrong direction. Sorry. Just a second. Oh, there. So these are only to show that when you can have something which is violating the Weiermann-Fraser law. I said that in our case we are interested not here, because maybe there are problems like you mentioned before, but here in the well-defined hydrodynamic regime, which is good for us if you try to reduce, to enhance the efficiency of the device. But maybe your comment is very pertinent here, but I know we're familiar with what's happening there. So, yeah, thank you for the comment. I will check. Okay. We can discuss on that later.
Thank you.
Any other question?
Hi, thanks for the nice talk. So you have this increase of the resistivity at low temperatures?
A decrease, you mean?
Increase of the resistivity?
No, a decrease. Let me check.
Wait.
Let
Sorry?
me.
No, you have an increase at low.
The previous one.
Yes.
There.
Yes, this one.
Yeah, on the left.
So the question is, imagine that we are, in this case, you are looking for the experiments, so for the best system to look at this behavior. Imagine that we are we find some experiment. There is an increase of the resistivity at low temperatures, and this can be to different reasons, to localization, to magnetic moments, to whatever. In which situations should we care about checking this type of effects?
Well, I should say that close to this regime, probably you need to care a lot about the semiclassical approximation. So I am not sure that in such a very low temperature regime, you can use more or less safely the Boltzmann equation. And actually, in the experiments, our coworkers are now seeing some clear signatures of the quantum behavior of Subnikov, the half, and many other things. Yeah, you are totally right. So we are not saying that we can explain everything with this. Clearly not. We know that. Thank you.
Any other comment? I have one. So I want to understand the Boltzmann equation.
Yeah.
The part of the electron-electron interaction.
Maybe there.
Yeah, it's probably this one is.
Yeah.
So if I understand just from the textbook, I'm not an expert in that. I'm not expert in anything. So you have two electrons which collide and they move. They are due to electron-electron interaction.
Yeah.
So in principle, the momentum is conserved.
Yeah.
So you should have some kind of unclap process in the
Yeah,
system
yeah.
with phonon
Yeah.
or something like that.
Well.
And that is going to change the center of mass, the velocity of the center
Yeah, sure.
of mass. And that corresponds, if I understand, to this the equilibrium. So you have to see the velocity of the center of mass of the distribution function. Yeah.
You're totally right. I mean, you can have effects of, well,
And this is the nonlinear term.
The nonlinear term
appear because
came here, for instance.
Exactly, because the mean free path of the electron in some
will depend on that. Yeah, that's true.
Okay, so I understand. So now, can you explain what means tomography in this equation?
Well, the idea is that we were dealing with this.
It's basically the velocity depends on the angular moment.
The mean free path
depends
sorry, let me tell you something. The idea is to play with this effective distribution function. We have only saying the number of electrons you have on different directions. So when you expand this function in terms of the modes, I mean Fourier components, we went to the literature, and some of the modes, I don't remember if even or odd, are essentially playing no role there. And the other half are dependence on the temperature. So you use that to take into account exactly this, because you have this type of collisions. But as I said, technical details are complicated. I'm not well familiar with that. But this is the idea, basically.
Any other question or comments? Yes, thanks again.
Thank you.